meeting going over and outlining the details of the Tiny Tapeout workshop series that we're going to start this year. I'll start with some brief society news, and then we'll get into the talk as quickly as possible. So we are the joint chapter, as I said, of the Solid State Circuit Society and IEEE CAS, or Circuits and Systems Society. We were founded on June 30th, 2020. And for the first couple of years, we were kind of hampered and slowed down by COVID. But in the last year or two, we've really picked up speed, covering a lot of talks across a lot of different topics. Last year, in fact, we covered many different topics in analog circuit design and LiDAR. For example, I have a slide that's more dedicated to talking about those things. But really exciting, let me get my pointer here. But a really exciting piece of news this year is that we're actually going to launch two different initiatives. Our biggest benefactor in terms of sponsorship in the last couple of years has been the Circuits and Systems Society, funding us for a lot of these exciting talks and workshops. And we're really excited to announce that we are fabrication flow and shuttle flow, actually. So we're targeting a tape out on this slide. You can see November 8th. And we actually have, several QR codes throughout the presentation and the slides that will be distributed separately as well on our website. And that application deadline to receive sponsorship for this tape out is on Labor Day weekend, or September 1st of this year, in lieu of a tape out in early November. Also, aside from the Tiny Tapeout, we're also sponsoring an Arduino hardware development contest, and it's actually not sponsored technically by us, but we will. It's sponsored by the Solid State Circuit Society, but we will actually sponsor participants for the material costs of the Arduino and the development platform, which can be up to $100. And we have another application, or we have the same application for that. We just ask that you complete it before the August 1st deadline of the competition if you'd like to get your materials and start developing in a reasonable time frame. So last year, we want to cover a little bit of last year. This was the scope of the talks that we had. So the CAS outreach program funded us for a sum of money that allowed us to have these three distinguished speakers come in and present on a variety of topics. So Dr. Swath I, from at the time the University of Idaho, he's since moved to the East Coast, gave a talk on low power analog and image sensor design that was extremely interesting. And he has 10 plus years of industry experience at photobit and micron imaging. He was around. His advisor was Eric Fossum, the inventor of the CMOS image sensor, and he just had a wealth of information to discuss in low power analog and image sensor type systems. Ohio State's own Dr. Marv White gave a very interesting talk as well. He's the inventor of correlated double sampling, and that was the focus of his talk, as well as the Emmy Award that he just won for the invention of correlated double sampling. So similar to the imaging experience from Dr. I, Dr. Marv White, was before Dr. I's time, but invented a technique, a signal processing technique that enabled a camera in every pocket. So he goes over the details of that and the history of semiconductors in general and the industry at large, which is very interesting. And then third, we had our last talk was a talk from Dr. Paul McManaman, who is a former chief scientist at AFRL and currently the president and CTO of Exciting Technology. He's a LiDAR subject matter expert, and it was a very interesting talk covering a wide range of LiDAR applications and techniques. All three of these talks are available on YouTube, and the links are through. You can see the links and the slides by themselves through our website. So we just wanted to mention this took place last year, but you can still view the content. Since last year as well, we've won an award through the Solid State Circuit Society. So we were lucky enough to win the Educational Chapter of the Year award, and our chair, pictured in this photo on the right, Dr. Rami Tantawi, was able to travel to San Francisco and meet Alvin Loke and other Solid State Circuit Society officers and accept the award, which was for continued workshops and outreach that we're doing through our chapters. So I wanted to mention too on this slide we have some contact information. If you have an idea for a talk or a workshop, we're all integrated circuit designers by trade. And the reason that we started this chapter was to have interesting talks and workshops that we ourselves find interesting and thought there would be overlap from others in the industry. So if you have a similar idea, we'd love to hear it. We would love to keep, the ideas flowing, and, as much as we can support it, we will through our chapter. We also have a new officer announcement. So Dr. Shane Smith is a research scientist at The Ohio State University. He's also president of a big sponsor for our chapter, Sensix Corporation. He's an IC design, test, packaging, and integration subject matter expert. And he's going to be our vice chair from now and for the foreseeable future. And stay tuned for a workshop from him over the summer on PCB design, and I'll cover more of kind of the framework that talk will exist in for it goes along with our outreach program this year with CAS. So now I'm going to talk about what we're going to do this year. So the name of our outreach program and the initiative is Foundations of Mixed Signal IC Design, and we intend for this to be a practical approach from lab to fab series. So Sam Ellicott, who I'll introduce in a second, is going to talk more about the Tiny Tapeout initiative and getting a chip out the door in this series. But there's a lot of other things that surround chip design in the way of board development, printed circuit board development, packaging, test plans and test infrastructure, instrumentation, all of those things. All of those things have to do with, once you're done designing a chip, getting it back and validating and testing it. So we wanted to build this series of workshops around, a comprehensive flow of the chip design experience. So aside from the Tiny Tapeout workshops, which we'll cover in great detail today and throughout two more throughout the rest of the year, there's also going to be sort of this peripheral knowledge that we're going to try to deliver to give participants more of a culmination of the entire view of a chip of what a chip designer does. So here's the opportunities for engagement slide or marketing slide that we've made for this. So we can sponsor you on either of these efforts. So on the left-hand side, you can see an Arduino starter kit, hardware development platform. These range in these could go from around $40 or $50 all the way up to $100. We're willing to sponsor that for participants if they fill out a sponsorship form. Once we kind of assess the funding levels that we have and gauge the amount of interest that we have across both these initiatives. On the right hand side, this is the Tiny Tapeout cost, and there's actually two numbers written here. There's a $150 number and a $300 number. There's an early bird special, so the earlier that you fill out this form that we're going to give a QR code in this presentation, the more we'll know how many participants are actively interested and have project ideas in mind, and the more people will actually be able to sponsor, because we're attempting to speak with some of the leadership of Tiny Tapeout and see if we can reserve space ahead of time for this. So please fill out the form and your availability as soon as possible so that we can get as many people on this tape out as possible with the funding that we have available. Here's the QR codes. Again, we will distribute these slides separately, and obviously the video as well. So we've been sponsored. CAS has been a big benefactor of us to this point. We for the last couple of years, as well as the Solid State Circuit Society and Sensix Corporation, all listed on this slide. But we are looking for more sponsors, as always. We will want to increase our footprint. We want to get more people involved, and we will want to be able to sponsor more people for interesting workshops like this. So if you're interested in becoming a sponsor, please reach out to us at the email listed on this slide. Okay, so I'd be remiss if I didn't talk about a new member initiative that's going on with the CAS right now. So if you have never held a CAS membership and you're an IEEE member, free memberships are available until August of 2024. It's not a huge amount of time. It's only a few months. But in that time, there is a lot of material on the CAS website, conference videos, workshop videos, tutorials. It's extremely invaluable, and at least give you a good sampling of what they have to offer, aside from what you can get through IEEE Explorer. It's a lot of content, and we sometimes will actually have workshops that are centered around some of the content that's on their free page. So If you're a student, the membership's only $11. So if you like it over the next 3 months, it's not too expensive to keep it going if you're already an IEEE member. But you do have to be an IEEE member for this. So wanted to mention this. This image is a link on the slide when we distribute the slides, so you can go to the page and sign up if you're interested. And then finally, we wanted to mention other opportunities for Open, who was formerly at Stanford and now is at the University of Hawaii, kind of legendary mixed signal, especially in the realm of analog to digital conversion and actually data converters. In general, he has a gigantic footprint in the research and the industrial space. He's putting on an open source hardware development program that's more mixed signal and analog and focused. They also do digital circuits. They use the open FA stock flow that's linked here on the slide, and there's a reference for it there. This is a little bit more rigorous of an open source design program. They still use the Sky 130 and actually the Global Foundries 180 open source PDKs as well, but they actually have weekly meetups, training sessions, and design reviews throughout the process. It's about a 5-month program, and the sign-up deadline is actually soon. It's next week. It's Friday, May 10th. I think it's a Friday. So if you want to actually enroll in this program, you don't have a lot of time to write it. But the only thing that's due next week is a proposal. And this is a very hands-on learning. It's a great opportunity to learn from, real subject matter experts in the mixed signal and IC mixed signal industry. And the program goes on. I think it ends roughly sometime in September or October. And that's when they get to tape out. Okay, so without further ado, I'm going to invite Sam Ellicott to come up here and give the rest of the talk. This is a Tiny Tapeout portion of the workshop. Sam, take it away.
Hello, I'm Sam Ellicott, and I'm going to be presenting on our first Tiny Tapeout workshop, which is going to be an introduction to Tiny Tapeout and sort of the design flow for doing digital design. A little bit about me. I'm the vTools coordinator here for the Columbus SSCS and CAS chapter for IEEE. I'm a PhD student across the street at the Ohio State University in the electroscience lab. I work in the circuits laboratory for advanced sensors and systems, the CLAS lab, and working in the area of RF and mixed signal integrated design, specifically in the area of designing true random number generators, which you can see a little figure of my design right down below here. I got my bachelor's of science in electrical engineering at Cedarville University down the road or near Dayton in 2019. And this coming summer, I'm an intern at Analog Devices. So just some of the goals for the workshop series in total is to understand the workflow for the open source tools. This is to demystify some of the steps required to generate digital designs, starting from an idea and working all the way down to getting it manufactured. It's a little bit daunting getting started in the area of integrated circuit design. Want to try and make it more accessible here. I want to give a hands-on introduction to digital design. So that's going to be a crash course in Verilog and the ability to test and design fairly simple little designs, but that you can build off of that to bigger and bigger designs as you advance. And then to accomplish that goal, we want to make a simple project throughout the series of 3 workshops. So even if you know nothing at the beginning, you can come out of this with a small but meaningful project. And then finally have some fun. So yeah. So today, this is what the plan is for the workshop series. So the introduction is today. So this will be sort of getting everything set up and some background information on how all the pieces fit together. Workshop 2 is we want to cover the tooling and the series project. So this is going to be mostly our crash course introduction to Verilog will be the second workshop in the series. And then workshop 3, we hope that you've made a project in the meantime between workshop 2 and workshop 3, and then we can hold some design review If you're having problems, we can do debugging on them and all of that. So that's sort of the outline of what we want to cover through the whole series. And some tentative dates, because I'm going to be gone this summer. The workshop 2 and 3 are going to be this coming fall. So in September, October, and November, October-November timeframe. So today, what are we going to cover today? So we're going to cover what are integrated circuits, a brief history of them, and then a introduction to digital design. What are we doing when we're designing an integrated circuit with Tiny Tapeout? And then finally, an introduction on how Tiny Tapeout works, like using the flow that we've developed in that third bullet point into how does that work with Tiny Tapeout. And then, yeah, so that'll be about the end of what we can cover today. So just a quick formatting note. Some slides I have in this presentation are more background knowledge, and you don't really need to fully understand in order to use Tiny Tapeout or make everything work. They're really here more for your edification and to provide some motivating examples and just sort of see how all the puzzle pieces fit together. But they're not required for day-to-day work. And they're going to have a title in red. And then if I have terminal commands, or like specific files later on, this is more in the end of the presentation, they're going to be I've tried to make them in bold italics so they stand out easily. Okay, so brief introduction to integrated circuits. So hands up, has anyone here used an app? I'm going to try and make it interactive, and if you have questions, interrupt me. So used an app. Who's written a computer program? This can be MATLAB, scripting. Okay, very good. That's going to be useful. Used an Arduino. Okay, most everybody, great. Designed a chip. Okay, few people. Has anyone ever, have your chip manufactured? Yeah, okay. And then finally, has anyone made their own chip in the fab? Like, yeah, Gus. Just Gus. Okay, so that's sort of like, okay, so decreasing levels of numbers of people have gotten into this. So some quick definitions on what is an integrated circuit. So it's called an IC or chip. The idea of an integrated circuit is that you have multiple transistors sitting on the same piece of silicon, and you can have wires connecting them together and to form complicated circuits. But that sort of begs the question, what is a transistor? So for a digital system, transistors are an electronically controllable switch. And things get more complicated when you're dealing with analog design. You have its amplifiers, there's nonlinearities, it gets complicated. But for the purpose of digital design and the presentation today and for Tiny Tapeout, a transistor is just a switch. And in reality, it kind of looks like that, but you can think of it as you just have a switch and you can control whether it's on or off with this terminal right there. So that's basically all you need to know for today. So why do we care about integrated circuit design? Well, I'm assuming most people here have a cell phone and you can browse the internet on it. That wasn't always the case. I'm a little young for this to say that, but cell phone technology has gotten shrunk. Things have gotten much, much smaller. And also they've added more and more features. And the reason they've been able to do that is by fitting more and more transistors into the same amount of space. So to look at a modern integrated circuit, this is a die shot of the Apple M1 Pro chip. We can, the stats on it say that there's about 33.7 billion transistors. It's about 16 millimeters square. And it's using a 5 nanometer process technology. So some of those numbers are really huge and really small. So to give a sense of scale, we want to look at, we can use this powers of 10 by Charles and Ray Ames. So a human's about a meter. If we go up in scale, 1 billion meters is the orbit of the Earth and the Moon. So that's when we're talking number of transistors on a modern large integrated circuit like the Apple M1, we're talking the order of magnitude of the Earth to the Moon, the orbit of the Earth and the Moon as being the scale that we're thinking about. Similarly, when we're saying something's in the 5 nanometer range, we're looking at the size of the proteins in DNA. So that's the scale of transistors in an Apple M1 chip is about the same size as a protein in DNA. So it's just crazy large numbers of objects that are incredibly tiny. How do we start making these transistors? This is a really fascinating topic in and of itself that I can't go into. All the links here are very interesting and go into a lot more detail on how they've actually been able to make devices this incredibly small. But just EUV is the technology currently being used to make the smallest transistors at scale. And it involves just crazy optics and crazy physics. So can't go into it too much, but it's a very interesting topic. So if you want to learn more, links here, and they'll be on the website. So with that covered, sort of the motivating example of why we care about integrated circuits, we'll go through a brief whirlwind history of integrated circuit design. So before transistors in the mid to late 1940s, to make calculating devices, people used vacuum tubes. So the ENAC machine, electronic numeric integrator and computer. So it was a programmable calculator for doing artillery calculations in World War II. So that's what they used to calculate trajectories. And they had a huge room full of vacuum tubes, which were, again, acted like switches. And they had to, the length of computations was bounded by how long before they broke. So they had to run around and switch out tubes while it was running. It was crazy. There's interesting history on that. The first transistor was in 1947, and I don't remember who exactly made it, but it was at AT&T and Bell Labs. It was called the point contact transistor. And from there, we moved to discrete transistors. So this is a die shot of a 2N2222, which you can still buy. But this is just a simple, it's called a bipolar junction transistor, which is the direct relative of the point contact. But we didn't stay there for long before we started to move into integrated circuits. This was the first integrated circuit that was invented by Jack Kilby in 1958 at Texas Instruments. Because we can see it's an integrated circuit because there's multiple transistors on a single piece of silicon. But notice how it looks pretty crude, where it's just the devices are just wired to each other with just little bond wires. So this wasn't commercially viable, but it was the first proof of concept of this technique. What we see is very shortly after that, in 1959, Robert Noyce at Fairchild Semiconductor made the first practical integrated circuit. So this picture is of a NOR gate from the Apollo guidance computer that was sent in. It was in the Apollo missions, and those were made by Fairchild Semiconductor, or at least designed by them, at least. But you can see here that we have multiple transistors on the same wafer, and we have metal contacts that are bridging the connections between the transistors that allows them to get more and more dense. And things just took off from there. So as time goes on, the number of transistors dramatically increases, and the size of the transistor dramatically decreases until in the 2010s, there's about 8 billion transistors in a processor. We can look at this. This is this trajectory is called Moore's law. It's the doubling of transistors on an integrated circuit about every 2 years, and there's reasons that it's a target that the manufacturers try and hit more than anything else. But what we can see is this 5 nanometer process is what the Apple M1 chip uses, and that's down here, and this is made by TSMC, Taiwan Semiconductor Manufacturing Corporation. We are using, for Tiny Tapeout, a 130 nanometer process, which was used for computers in the early 2000s. But it's still useful. Even though it's an old technology, it's still useful. It's very mature, and it's useful. It's used widely in doing analog design. Less so for digital, but it's much lower cost than using, say, something at this range. So very inexpensive, very high performance. Very inexpensive and then very high performance. And there's a big transition in around 2015 to FinFET transistors where things had to go really crazy so that they could keep shrinking transistors. And that's just a fun bit of, there's a lot of interesting technology and history there. So I recommend looking into that if you can. So the other thing is, as we shrink the transistor, the increase in, if you can increase the number of transistors, that means nothing if they maintain the same amount, if it takes the same amount of power to use them. So you also have to decrease the power density. So that's just another side of the shrinking of the transistors. So if we thought about it in terms of looking at automobiles, what if Moore's law applied to automobiles? So if in the 1960s, there's like 170 miles an hour is the top speed, and gone up to about 300 in 2020. If we had a Moore's law car, we'd be able to go 80 million miles per hour, or meters per second, I should say. And we could go 15,000 miles per gallon. So the amount of scaling that we've been able to get out of transistors has just been completely insane. So it's just kind of a look at how sort of exciting this area of research is and doing designs in this area. So for further information, since this was just scratching the surface of this topic, I recommend looking at Professor Marvin White's talk that he gave here. He knows the history of this better than I think anyone in this room, because he was there as like they were in the development of the integrated circuits, and he has some fun stories from that. There's a good PBS documentary on Silicon Valley, and the Asianometry YouTube channel does really good dives into the history of lithography, manufacturing, and all of that. So I recommend those resources if you're interested in this topic. So with that, I want to go to more of the heart of this presentation, which is an introduction to digital design. And once again, if you have questions, feel free to interrupt me and ask them. So what are we trying to do when we make a digital design? Well, the idea we're doing is we're trying to take a concept, some algorithm or behavior, and then we're going to try and turn it into some sort of physical implementation, so physical gates. So let's say we had like an encryption algorithm. We're trying to take data from plain text and turn it into ciphertext. We're going to run it through something, and at the end, we're going to get out physical gates, and that we can get these made, and then when we get the chip back, we can put our plain text on one side of it, set of inputs, and we can get our ciphertext coming out on the other set of outputs. So it turns out what this is called is the digital design flow. And for doing open source designs, this flow is called OpenLane. So I want to go a little bit into explain how this process works. So I think it's a good illustrative example to look at a simple problem. So what if we wanted to calculate the nth Fibonacci number? And what if we wanted to do it with software? So I don't know if you can see the screen. It's a little bright in here. But if we want to calculate the nth Fibonacci number, we just write a little program to do that. It's pretty easy. This is just a little C program. You can go to this link and you can actually have it compile. And we run it through a compiler. So in this case, GCC, and we're going to get assembly out. So people here have done programming. If you wanted to think about if I just gave you a piece of code, and how would you figure out what it does? Would you, Run it? Okay. What if it doesn't work? What if it doesn't compile? What do you do if you're debugging? Yeah. Well, okay. Yep. But yeah, you said it line by line. So you go through one line at a time, right? So you like say, look here, and you just kind of keep going line by line. So hold that in mind as we like go through this, because this is a big difference between software and hardware, is this line by line thing. But same with assembly code too. Like you could figure out what this is doing by like going through, looking at this line, seeing how it modifies the state, et cetera, right? Make sense? Okay. So what if we wanted to do this in hardware? So for digital design. So in digital design, what we're going to do is we're going to take code in what's the form of a hardware description language, in this case Verilog. We're going to run it through what's called the synthesis tool, and for the open source flow, it's called IOSIS, and it's going to spit out for us a representation of that design in using digital logic gates. So this is what the design looks like. So you take code, we run it through this tool, and it spits out logic gates for us. So, and these gates are generic logic gates. They're not mapped to any particular implementation in hardware, because if you think about it, like if we're using like the Skywater 130 process, that's sort of different from using the TSMC 5 nanometer process. There's going to be changes between those two implementations. So this is just generic. It's at a very high level of this implementation. So, we're talking about gates, but what is a gate? So there's sort of the Legos of digital design. So you're given a set of them, and then you can work from there. So there's two forms of gates at a high level. There's combinational logic gates. So these perform some sort of digital logic function, so like and or not. You have like a set of them over here. And then we have sequential logic. So these are memory elements. They're also called flip-flops, and they store data for a clock cycle. So when you're looking at it, if you have a piece of data that's on your input D, it's going to hold the previous data that it's had on its output on Q until it sees a rising edge on its clock pin. And then when it sees a rising edge, the data is going to move from D to Q, and it'll hold that until the next rising edge of the clock. And in this way, you can store the state of the system as it executes. And this lets you hold on to things. So that all makes sense? Okay. So yeah. So when we're writing Verilog, what are we trying to do? So what we're trying to do is we're trying to behaviorally describe the gates that we want to generate. So we can, so what we want to see is we want to see a set of combinational elements and a set of sequential elements that get mapped into the actual output hardware. So, we'll look at this. So we'll start with our Fibonacci example. So we have a set of signals in our system that we want to implement. So we have like our reset, our clock, some things that give us control over the system. And then finally, our input, so our input n, so this is the Fibonacci number that we want to calculate, and then an output that is the resulting value. And then we have 3 state variables that we need to keep track of. So we can say that all our inputs are into the system and our nets, they're wires. So we can see them implemented in this hardware here. And then we can hold on to the state in registers, and we can see how those get represented in the block diagram that gets generated for us here. So we have our current, our next, and our iteration state. So we also can, in Verilog, we can generate purely combinational logic. So those take the form of these assign statements, and you can, every statement in Verilog, each of these assigned statements gets evaluated in parallel. So there's no ordering. If it doesn't matter where you put an assign, it's going to get executed theoretically at the same time. The simulator doesn't necessarily do that, but in hardware it does. And then finally, we need to define what the next state that our sequential logic is going to hold on to, and we can do that in an always block. So here we define what the register behavior is going to be for the next state. We assign to it on the positive edge of the clock, and it's only evaluated at rising edges. And then if you have multiple of these blocks, all of these are executed in parallel as well. That all make sense? So the other thing to keep note of is that if you're in one of these always blocks, they get, you can think of this like code. These are executed in series. So things at the top of the always block are low priority, and things at the bottom are at a higher priority. Because if you assign to a register up here and then assign to it later down here, it's basically like this assignment just never happened. So you can sort of get complacent when you're writing things in always blocks. It can feel like normal code, but don't get complacent. You have to really think about it like, what am I generating in hardware? At least that's my trick. So you can also see here that you can generate combinational logic in the always block. So you can see that we're generating this little bit of logic here in this statement, and we're doing these adds here, which are a combinational element. These are getting generated in this always block as well, and they're kind of feeding back and making this little state machine. That all make sense? So here's just a simple example of once we have a block diagram, how does it execute? So how does the system evaluate over time? So if we're looking at the system and we start it up, so we have the inputs. We've just started the system up, so we don't know what our output is yet. We have our inputs 0, 0, and we don't know what the outputs of our flip-flops are, and we don't know what this is yet either. So at this time step, if we applied a clock signal to this right now, what would the states of all of these outputs be? Well, so if we have a clock, so some of them will be random, but not all of them, right? So like if we have applied a rising clock signal right now, what would A prime be? Yep. What about B prime? Yep. And then Y? Yep. Okay. Yep. So what we see here is, yep, exactly that. Exactly what Darren said. So we'll see if we have a rising edge here, we'll transfer the state from the input to the output for this first flip-flop. We didn't really know what the input at this point was yet, so it's still unknown. But after this, we have our 0 here, our 0 here, and this is a NOR gate. So if both inputs are 0, it outputs a 1. So that's what we see here. So this makes sense. So this is what we're doing when you're following a digital logic. So okay, now if we apply a 1, 0 here, what's all of our outputs going to be? And once we apply our next clock. So what will A prime be on our next clock cycle? 1, okay. B prime? 0, okay. Yep, very good. What will Z be? Yep, and then what will Y be? Yep, okay, very good. So yeah, so that's what it'll be. That's what it'll look like there. So you can sort of just keep doing that for each of these states. So it turns out that since that's a NOR gate, each of these next states is going to all be 0. So this is sort of how you go through the system diagram once you have some digital logic, what your outputs are going to be. And what we'll see is when we're doing debugging, we'll be able to see this. We won't necessarily be able to see this so easily. So it's useful to be able to look at one of these timing diagrams and figure out what's going on into the internal state of the system. That'll make sense? Okay. So here's we get into something for edification. So how do we actually make a logic gate? So logic gates are made out of transistors. So they come in basically 2 flavors. You have PMOS and NMOS. So they're sort of flipped from each other. So a NMOS transistor, if you put in a 1 on its input, it'll be a closed switch. A PMOS transistor, if you put in a 1, it'll be an open switch, and sort of vice versa here. So NMOS you put in a 0, open switch, PMOS you put in a 0, closed switch. So using these building blocks, what we can do is we can make digital logic gates. So this is a NOR gate. This is a NOR gate made out of transistors. So if we put in an A and B as being both 1, we can see that we're turning both of these transistors on, and this output's going to be 1, and both of these transistors are going to be off. Similarly, if you put in 1, 0, so this transistor will be off, and this transistor will be on. But since there's no way for current to flow here, then this will be dominated by these 2 devices. Since A is on, this device is on, and it gives a way for current to flow here, and we can pull this down to 0. Makes sense? And you can sort of follow that throughout the logic diagram, so you can get this truth table output for this gate. So this is how a gate gets made. Don't have to follow this, This is mostly just to see how do you actually build a gate with transistors. If you look at what this looks like physically, when we do if you actually like opened up the design and we're able to get a microscope and look down at what it's made out of, this is what it looks like. So you have M1 and M2, these two PMOS transistors are up here, sitting up here, and there's no wire between them, but they kind of go underneath into the actual silicon. And then down here is you have the M3 and M4 NMOS transistors, and you can see how it's tied. So this is your A input and B input, and this is your Y output. So that's kind of cool. So finally, so we're going to mix things out of these gates. So these are our building blocks. Skywater, the 130 nanometer PDK that we are using for Tiny Tapeout, gives us all of these gates for us that the tool can use in order to make our designs. So we have all our combinational logic gates. That's a NAND gate. So it looks something like that. And then we have our flip-flops. And the flip-flop is way bigger. It's actually about 5 times bigger. So this is something that is probably useful to keep in mind when doing designs, is that combinational logic, each individual combinational logic cell is way less expensive than a sequential logic cell, because this takes up about 5 times as much area as that does. And when you're doing Tiny Tapeout, your areas, that's the main constraint that you have, is that your area limited. So if you can reduce the number of flip-flops in your design, you can fit more in. Yeah, usually is the cost of speed. Yep. Was there a question? Sorry. Okay. Sorry, I heard somebody. Okay, so once you have a gate, you need to wire it up. So the Skywater, the process technology has layers that you can build transistors in. That's down here at the silicon level. And then it has layers that are metal layers that you can connect your transistors with. And the Sky 130 process has 5 of those metal layers. So what will happen is when you're building, the gates themselves have metal that uses this in between transistors in the gate, and then it goes up to here for power. So what the tools will do is they'll plop down all your gates, and then they'll put wires between your gates on these metal layers. And that's sort of how your chip gets made, is you have a tool that takes your design, it converts it into gates, and then you can, convert between them. So differences between software and hardware. So can anybody name differences from what we discussed, the differences between the software and the hardware? If you took both of these designs, how would you think about debugging? How would you think about going through and reason? Oh yeah, go ahead.
Software is like sequential, at the top is least important.
Yep. Yeah. You go through the software. You go through line by line and sort of see how it evaluates. What about in the hardware? What would you do? Mm-hmm. Yep. Yeah. Exactly. Yeah. I think you're on the right track. What? Oh, okay. So you look at, for people online, what you do is you could look at each node in the system, and you would have to evaluate it at each time step to make sure and to see what the next output is going to be after your next clock. So that's how you would look at this. So like another way you can think about that is every one of these hardware blocks is always running. So you always have to care about what the input and output for each of these blocks is going to be. And you'd have to look at that right before you have a clock cycle. So that's sort of the main difference there. So the software executes sequentially, and then the hardware is always running. And this actually gives you some interesting performance insight into why is hardware faster than software. So for software, you can only really, technically false, but you could really only run one of these at a time. In hardware, you could just whack down another copy of this, and you could run it at the same time. So you're trading off, but there's always a trade-off with that. If you whack down another one of these, you've just done what? Yeah, you've parallelized it and you've doubled your area. So you have a speed space which is at the end of the day, cost concern going on with that. So that's sort of the idea that's going on with that. So to recap, so when we're doing digital design, we're going to take a concept, some algorithm behavior, and we're going to convert it into some physical implementation. So we have our software, and we're going to run it through, and we're going to generate generic gates. We're going to convert those generic gates into standard cells that match the process that we're using. And then we're going to connect up those gates and do place and route until we have a final design that we can actually build. Make sense? Okay, so how this relates to Tiny Tapeout and doing the open source flow is we have our input design here. We're going to run it through this system, and we're going to get out an output, which is in the form of a GDS file. So we'll break this diagram down a little bit. So this first step right here is elaboration. So this is conversion into the generic gates. Then we run through synthesis, which is converting those generic gates into real gates that we can whack down into our design. And then we have a place and route flow, which places all of those designs in the silicon and routes little wires between them so that they can talk to each other. And then finally, because I didn't quite mention this too well in the beginning, but when you're actually building a design, since everything's so tiny, there's a lot of rules related to how far things can be apart from each other, how far your wires can be from each other, how long your wires can be, all of that. And those go into design rules. And you have to make sure that all of those design rules are met before you can actually get your chip manufactured. So what the sign-off process is making sure that once you've gone through this flow, your design A still works, and B doesn't violate any of those rules, and they can actually get it built. That it's not going to break any of their machines as they try and build it, and that when your design comes back from getting made, that there's not going to be any broken wires or anything like that. So yeah, so that's the sign-off process. So luckily, Tiny Tapeout via OpenLane handles most of this for us. We really only have to worry about this first bit of the process right here, which is making sure that our input design files into the system actually do the thing that we want them to do, and B, that once we've put them through that first step of the process, it turns into something that makes sense. So you can make a design that technically behaves the way that you think it should, but it generates just huge amounts of spaghetti hardware. And you don't really want that because it'll have bad performance and you can have weird errors and stuff like that. So really all we care about is that we have a design that if we run it through a simulator gives us the output we expect. And B, that once we run that simulator through that elaboration step, we get a generic design that looks about right. So that's really what we need to worry about when we're doing this digital design. So I said our output is in the form of GDS. And just to give you sort of an idea of how big a design is going to be when you put it through this flow. So all of these little squares here are 70 by 70 micron. So we have a binary to decimal converter that's about 25 standard cells. An 8-bit counter is about 50 standard cells. And then a 4-bit counter and binary to decimal converter is about 50 cells. And those all fit comfortably in that 70 by 70 micron square, 70 by 70 micron area. So this is kind of gives you a sense of how many cells that you're going to use in a design and how much area it's going to take up. So what did we, oh yeah, go ahead. Yeah.
Yeah, the slide before this. So even synthesis gets handled by Tiny Tapeout?
Yeah.
So all you have to do is just the code and simulation.
So what we put into Tiny Tapeout is that we make some Verilog source files here. And we sort of drop them into, it uses GitHub Actions, and we'll get to this in a little bit. But you just drop your Verilog files into that, and it will spit out for you a GDS file. Yeah. And it'll actually spit out, you can actually make it do the simulation for you, but it's a lot nicer to do it on your own laptop because then you don't have to wait 5 minutes to see that you had a syntax error. So yeah, that's sort of the idea. It really handles a lot of this stuff for us, and it's pretty nice in that. Makes it really easy. Yeah, no problem. Okay, so what did we learn? We have a design, we run it through the digital flow, and then we get a physical implementation out. When we're doing digital designs, our digital designs are made up of gates, and there are basic building blocks. There are Legos, and then we have those gates are split into two types. We have combinational and sequential logic, and then finally, what we're trying to do when we're coding up a design is we have Verilog, and that lets us describe those gates in terms of code. The digital flow, what it does is it runs these 4 steps. We have the elaboration step, where we're taking our HDL input and converting it into generic gates. We have our synthesis step, where we're generating real gates from those generic gates. Place and route, where we whack down our generic or our real gates and connect them to each other. And then finally sign off, where we make sure that everything still works at the end and that we can get it manufactured. So with that, I think what time is it? 7:04. I think Rami said you want like a 5-minute break or so? Okay. Okay, as people wander in after grabbing more pizza. Okay, so now we can move on to applying like the general knowledge about the digital design flow. We can apply that to actually building things into Tiny Tapeout. So how does Tiny Tapeout work? So it's basically a cloud-based design. So it runs that whole open lane flow in GitHub in a set of GitHub actions. So this is really nice for us because it means that we don't have to install or download any of these tools. It gives you a really fancy 3D viewer and explorer. And I have a little example design to check out for later. So this is what a chip in Tiny Tapeout looks like. So this is one of their designs, which is not very filled right now. But it basically segments the designs into 500 of these little tiles. And so that means everybody's design can get merged onto this one chip. So this significantly reduces the cost. So normally getting a chip this big on the SkyWater 130 process is about $10,000. And that gives you about 100 chips. So it's not extremely expensive in terms of chip design, but it's still a fair chunk of change. But when we're doing it with Tiny Tapeout, since everybody's project gets merged onto this one die, it's able to reduce the cost to like $150 to $300 per tile. And that includes all the extra stuff they give you too, like the PCB. So it also gives an opportunity is if once you get a chip from Tiny Tapeout back, you don't only have your design, you have everybody else's Tiny Tapeout design as well. Because you're on these tiles and they have a way to like take the output from your tile and then route it to the output, and then you can test their design too. And so you can just flip a couple switches and test everybody's design. They also give, okay, so yeah, this is just a zoom in on what those tiles look like. So this is a single tile, and what you can see here is that you can actually get more than one tile. So you can buy up to one full row of these tiles and it's like $50 a tile if you want to add more. So that's sort of how that works. So the idea is basically you have your design, it has a defined set of inputs and outputs, and then they'll route your design to the edge of the chip so that you can test it. That's how that works. And then they give you a PCB too. So this is sort of how that all fits together. So when you get a Tiny Tapeout back, you get a chip that they've put on a carrier board, and then a test board that has like PMOD inputs and outputs that you can hook external parts to. So yeah, so that's sort of Tiny Tapeout, what it looks like. So this is what Tiny Tapeout looks like when you're just looking at a single tile. So a single tile has an area of 160 by 100 microns. So not a huge amount of area, but not unmeaningful. That's enough to fit about 1,000 logic gates. And you can, as I mentioned before, you can buy more than one tile. You can buy up to like one full row of those tiles. So these are the pins that you get with a Tiny Tapeout block. You get a clock input, which can run up to about 50 megahertz, a reset, 8 inputs, 8 outputs, and 8 bidirectional inputs, I/O. So it shows up as these optional inputs here in this diagram. But what happens is when you set these pins here, it basically, if you put a 1 in on like pin 7 here, that means that the pin 7 here is going to actually be an output that's connected to something, and all the rest of them are inputs. So that's sort of how the physical interface of Tiny Tapeout looks like. So you have to make a design, when you make a Tiny Tapeout, you have to make a design that matches this profile. So this is like the limitations that you have. You can really only have up to 16 inputs and 8 outputs, or 8 inputs and 16 outputs, something along those lines. So that's how, sort of how this fits together. How you actually do a Tiny Tapeout design, you can use this design simulator called Walkway made by Yuri Shakit. And it's an online simulator that exports Verilog code that then can be put into Tiny Tapeout to generate a design. It's pretty neat because it's a live simulator that runs on the web. You don't have to install anything. And there's some examples to do that. The issue with doing a design this way is that it really limits how big you can make it, because you have to place all of your gates manually. There's no like you can't make a sub block real easily. So you're kind of stuck just placing everything manually. So there's like a complexity limit to how far you can go with something like this. So that's, I'm mentioning it for the sake of completeness, but probably don't recommend using this for doing like an actual Tiny Tapeout. It's fun to try out though, and to sort of get a feel for how the system works. So this is how you use Tiny Tapeout in terms of writing a Verilog design. So Matt Venn has a large number of tutorial videos, which I've linked here, and there's on the Tiny Tapeout webpage. I have the example project that I'm going to sort of be working with, and that I've sort of hinted at here. We'll get into second workshop. We're getting to a more meaningful example project. This one's just really nice and easy, self-contained for right now. So when you're doing a Tiny Tapeout, what you need to do is you need to make a new GitHub repository by using the template provided by Matt Venn and the Tiny Tapeout team. The project needs to be public, and you have to enable GitHub pages in order for it to work with Tiny Tapeout, because basically how Tiny Tapeout does is it kind of like hooks into GitHub and pulls out a design from it. So if it's not public, they can't access it, and if they don't have enabled the GitHub pages thing, it can't actually generate a design for you. So you have to have those set in order for this to work. And this is all covered well in the tutorial video too. This is here for the sake of completeness. And then what we're doing is we're going to update this info.yaml file, and that is going to include the top Verilog module. So these are from the pieces of code that we write in Verilog. It's going to include all the source files that we write, and then area. So since we can buy more than one tile, it defaults to 1. But you can, if you run out of space, you can say, I'm actually using 2, 4 tiles, whatever. And then some documentation, since when you get everybody's design back and you don't have any documentation, you have no clue how to use it. It's basically strongly encouraged that everybody writes some reasonably good documentation for their project, so that when you get a chip back, you can test your design and other people's designs too. So, and then that's also in the docs. So with that, I'm going to see if I can make this live demo work. So if I go over to here. So, okay, yeah, here we are. So this is what Tiny Tapeout looks like. Let's see. Yeah, there we go. Make that full screen. So this is this Fibonacci sequence generator code. So here I have just like a little bit. This is on GitHub, and this is linked in the slides and on our webpage. But we have this design here, which generates that set of Fibonacci sequences. So if we can go into our source code, we can look at, so this is the interface to Tiny Tapeout. So here we have the name of the design right there in this module for Verilog. We have our inputs that Tiny Tapeout uses. So we have our in, and they're labeled the exact same as what Tiny Tapeout has, and that's important. And then we're hooking up our submodule right here, this fib piece of code. And this is where the actual design is. So if we look here, this is the fib module, and this is basically what I copied, and this is what was in the PowerPoint presentation earlier. So it's just all of that right there. So that's the Verilog code that we're using to make this. Then we can go over to the tests. So we have various test benches here. So the main one is here is this test tb.v. So what we do is we'll get into this a little later. Actually, I'm gonna go back for now. Yeah. So go. Oh, Control plus, I think. Yeah, how's that? That better? Okay. So that's sort of that's the source code, and we already kind of had a quick look at that. When we're editing this info.yaml file, this has some basic information here. So this is what Tiny Tapeout needs to actually sort of figure out how to build our design. This is basically what tells OpenLane what files that we have, where our Verilog is, how, and sort of that sort of basic information so that it can run that flow for us. That makes sense. So basically, all we have to do is say, well, we have our two files that we have Verilog in. They're right here, listed under source files, right there. The name of that top level module is right there. So that corresponds to the name of this module right there. So that's basically all Tiny Tapeout needs to know in order to work. It'll get mad if you don't have some documentation because, once again, they really want to encourage people to actually document their projects. But yeah, and there's the number of tiles. So that makes sense. So now we can go and look at how Tiny Tapeout runs. So that runs into this GitHub Actions thing. So we have basically three things that Tiny Tapeout runs. It makes docs, and it runs a set of tests on your design to make sure it's working the way you say it should be working. And then it makes you a GDS file that you can have to get manufactured. So we'll start by looking at the docs. So that was probably not smart, but it generates for you a data sheet, which is hard to see, but oops. Then F11. Okay, I guess we're not going to see the data sheet, but yeah. So it generates for you a data sheet that you can use that's going to be provided when you get a Tiny Tapeout back with everybody else's. That's the docs flow. Then there's a test flow, and so this is running the Verilog test bench that you provide with your design, and we'll have a look at that in a little bit. So what that does is it runs and it generates you what's called a VCD output, and you can plug this into a simulator and look at the waveforms coming out, and I'll pull this up in a minute to have a look at that. And then finally, it generates a GDS output. And so this one's probably the most interesting looking of all of these. So it runs a few actions. So this GDS action is Tiny Tapeout running OpenLane. So it grabs the input files and then it runs through them. So you can look at the build logs. So this is it installing a bunch of stuff because it's a Docker image and it's compiling a bunch of stuff. Yeah, there we go. So this is the output of OpenLane as it's running. So yeah, so it runs through a bunch of those steps, and it's that step by step in the block that we see in the block diagram. And it'll complain if it gets an error, but right now it's running okay. So we get an output for this. This is what produces the GDS file. And then, oh, okay, is there a question? Yeah, just interrupt me if you have questions. So I'm not going to see you otherwise. Oh, yeah, GDS file. And so then what we can see is, since it finished successfully, we get this output. So this tells you what all the gates it used from the Skywater 130 process and how much area it used. So it used only about 9.3%, and it has about 24 flip-flops, which is about what we expect because we have 3 8-bit registers. So 3 8-bit registers means 24 flip-flops, so that makes sense. And then there's some combinational logic to do the rest of the math in there. And then with that, oops, we can look at, and then it generates for us a preview. So this is a 2D preview And then it will also open up for us a 3D preview. It'll load. This is a little awkward on a touchpad, but yeah, so that we have a 3D preview that we can do, and we can turn on and off various metal layers and have a good look at the design. So yeah, so that's sort of, this is sort of what Tiny Tapeout does, and how, like, sort of how it fits together in terms of the GitHub flow. So what you do is you basically just push your code to GitHub, and then it'll run through all of this for you. So to actually, to generate all of this stuff. So let's see. So does that all sort of make sense? Like how that fits together? You basically just, it's just basically how GitHub works.
Yeah, I have a question. How do you run a test bench for like a functional simulation?
Yeah, so go over to code here again. So when you put into Tiny Tapeout, there's this tests folder or test folder, and what you do is you provide it a tb.v. The one that you really need to run the simulations in the clouds is pretty small. So all you need is you need to have these lines right here, so it generates you an output that you can download later on. It also needs, you just define some registers, and then you basically hook up to your top level module right here. And you define that, you hook up your inputs to those registers you defined up there, and it'll run. And then Tiny Tapeout runs what's called CocoaDB based design test bench, which is a Python based test bench language. So you can hook into, basically it will do the elaboration step on the Verilog, and then you can hook into that with Python and run write all of your tests in Python. This works well when you're doing the GitHub Actions on the cloud, but unfortunately it doesn't work well with Windows. So if you want to run simulations locally, you can't really use this flow. Yeah, go ahead.
That you can actually run simulations remote?
Yeah.
Okay, they have a cloud infrastructure for simulation. Okay.
Yeah. Yeah.
Quick online question. Pad frame is automatically taken care of by the foundry.
Yes. Well, we're not even, our design isn't big enough to be handled by a pad frame, to be honest. Like Tiny Tapeout has like its own MUX architecture that you're getting hooked into, and then they're hooking into the foundry pad frame. So that's how that works. Yeah. So you basically just have to define Verilog pins, and those get hooked up via Tiny Tapeout. So, yep.
It may be that the place and route tool. It may be that the place and route tool knows where the MUX is or the bus is, and then takes care of, once you specified your I/O, putting it next to that.
I believe that's how it works under the hood. Yeah. So yeah, this is just the CocoaDB test bench. So we're initializing stuff, we're running it. And so in this case, in this example, we're running the first 5 iterations of finding the Fibonacci sequence. And we're also comparing that to one that we're calculating just directly in software in Python to make sure that they match between each other. If you're running simulations locally, you need to write a Verilog test bench, which is basically the same thing, but written in Verilog. Yeah, there's probably a good way to unify those two, like either have basically nothing in the CocoaDB test bench to run the Verilog test bench in the cloud. That shouldn't be too hard. I just kind of ran out of time when I was putting this together to like make that work nicely. So we're going to be looking more at Verilog test benches in a minute. So yeah, so that's sort of how that fits together. Any other questions on this?
So Sam, as people going through the flow to make this happen, and they have questions, did you talk about resources?
Yeah, no, I'm going to go back to the slides in a minute.
Okay, so there will be.
Yeah.
Thanks.
So yeah, but is there anything in the code that people want to see while I have it up right now? Is this all sort of make sense? You good? Okay. Okay. I'm going to go back. Oh,
Oh, it's fine, I got it. It's a clear question.
okay. Okay. So slides. Skip the demo. Okay, there we go. Those are my backup slides in case that didn't work. So, yes. So Tiny Tapeout, we can run cloud-based development. We can do the full flow in GitHub Actions. So like we can run our test benches in the cloud if we wanted to. We're running GDS in the cloud, so we're generating our output files like that. And we really only need GTK Wave, which is the waveform viewer, if we want to do debugging. So as we saw when we were running that test, it generated us a file that we could download. And that file will fit into this waveform viewer that we can use to do debugging. The one problem with this is it has a fairly slow iteration loop. So you have to push your code up to GitHub, wait for it to run the test, like set up all the tests, and then run them again. So it can take like 5 minutes before you learn that you made forgot a semicolon, which is really annoying. So for that reason, I think it's beneficial to run some simulations locally. We could, if we wanted to, run the whole open lane flow locally. So this would get us a GDS file as our output on our local computer. The
Hey,
issue with,
Sam.
yep.
Sorry, real quick. Online question. Do the tools support physical simulation and timing?
I don't know about timing as much, but yes, for physical simulation. So if you have a test bench, like the CocoTB's test bench in Verilog to run pre-checks, once it does the synthesis process, it will run a gate level check on you as well, which will also give you a pass-fail result to make sure that that's still.
You showed in the flow that it does STA, CTS, and it does.
It does. Yes, but I haven't looked at the logs for the STA analysis. I think it must do them somewhere in the background, but I don't know. I don't think when you look at the GTK wave view, it has all the STA in there as well. It's just the gate level. But I think if you look at the log file from the GDS flow, so there's one of the downloads is a set of log files, which also includes your GDS file, I think. That probably includes the STA in there. I'm not 100% sure about that, though. Yeah. Okay. Yeah. Can run this whole locally, but it's big. It's about 10 gigs. And I did not want to even try and get this working on Windows because I got it working on my computer locally, my Linux computer, but getting it in, it has a lot of Python dependencies that I don't know if have Windows installs for them. So I don't really want to try and debug that. My solution, and I think what was probably the most beneficial, is to run simulations locally. So this means that we're going to develop the Verilog files locally, and then we're going to install a smaller subset of the tools that allow us to do the elaboration process and a little bit of the early stages of the synthesis process, and so that we can basically write our Verilog test benches and code, and then elaborate and simulate from there. And then that's a much smaller download size. It's only 1.5 gigs. And then we can simulate our Verilog HDL and get our basic functionality working. And then we can push that to GitHub, and it'll run the rest of the flow for us. And then, yeah, harden with Tiny Tapeout flow. So the basics of installing the tools is all here. I'm not going to go through this in too much detail right now because you'll have the slides. But the basic idea is that we're going to install this open source CAD suite. And these are just binary releases of the open source tools. And you can extract that to a file path without spaces. And this gives you GTK Wave, which is your waveform viewer, Icarus Verilog, which is your a behavioral elaboration tool and simulator, and then Yosis, which is the elaboration tool, that real elaboration tool, and etc. And then what it does is you basically extract this archive, you double click the start.bat file, and it generates you a terminal from which you can run all of these tools. Yeah. So, and for this to all the work, you also need a good text editor, so like VS Code and Git. So I'm not going to go into how to use those because there's plenty of good resources from the software world to use both of those tools. If you're running local simulation, what you do is you, in an open source CAD suite terminal, you start up the terminal, you type in, like, say, GTK wave, and then it'll start it up for you. And from there, you can just like import the VCD file that you want, and it'll pull up the waveform. To run simulations, what you can do is you can run Icarus Verilog. So iVerilog, you put in an output file, you put in this little thing, which is something I put in for test bench reasons, and then the list of Verilog files that you have in your design, and it'll generate you a command or like a piece of simulation code. If anything is wrong in terms of the syntax of your code, it'll complain right here. And then when you run this command, it'll actually simulate your code, generate you a dump file, a VCD file that you can put into GTK wave, and it'll print any output that you have in your test bench. So there's some information on how to use that. And then this is a little bit more information on how the test benches are set up. So you need in the top of your test bench, you need to put these couple of lines of code right here so that Icarus Verilog knows that you should generate a file output that you can use to look at your waveforms. We need to define a set of variables at the start that correspond to the Tiny Tapeout inputs and outputs so that we can check those inputs and outputs in our actual test bench. We need to instantiate our Tiny Tapeout module. We have right here, this is for doing the gate level testing. So when you're doing gate level testing, you actually have power pins going into your gates as well as your actual signals. So when you're doing gate level testing, those have to be connected as well, but they don't exist when you're doing the generic gates. So you have to have that behind a little like definition like blocker. And then you just hook up all your gates to each other. So, and then if you run that with the example project I have, you should get a result that looks like this when you plug in your VCD file into GTK wave. What we can see is we start off by, how this system is put together. We put in this strobe signal, and this tells the design to start generating a Fibonacci sequence number. And then when it's done generating that number, it generates the busy signal goes low, and then we can read our output right here. And we can do that again with a higher number as our input. So this is the number that we were trying to generate. So if we're trying to generate this 3, we'll strobe the signal, and then it'll wait quite a bit longer before we get our result. But once that busy signal goes low on our rising edge of the clock, we have our output result for us to view right there. So we have this, if we look at the Fibonacci sequence, we have 1, 1, 3, or 1, 1, 2, 3, 5, et cetera, et cetera. So yeah, so that's sort of how that fits together. And I can run this because I have this on this right here. So I can open up command prompt, CMD right there. So I can go over to here and go to D drive. Yeah, because it's a Windows path. Okay, there we go. CD OSS CAD suite. Oh, yeah. Tiny Tapeout workshop resources. CD OSN. Oh, wait. Why did I do that? I can do this. Click that, and I open up a terminal window with the tools started. So now what I can do is I can open up. Well, actually, I'm going to run the simulator for everybody here first. So I can go over to here, and I have the GitHub code already downloaded into this thumb drive. So what I can do right here is I have the code for that, and I can just drag that over to there. I can go home, and I can CD into that. Okay, so now I'm in the folder from GitHub, and so I can run Icarus Verilog. So I can run iVerilog -o tb VVP-I Icarus. And then I'm going to put in all of the Verilog code files that I need.
So, real quick, should all the design files be Verilog besides the top, or can you be able to combine VHDL and Verilog?
I don't think Tiny Tapeout has VHDL support right now. It might, but I don't think so. You'd have to ask. We'll get when we get back to the slides. There's places to ask for help. You can ask on like the Tiny Tapeout Discord forum how that's supported or not. There might. I think there's support for system Verilog, but system Verilog's a little bit more hit and miss in the tools. Verilog's the best supported HDL language. And there may or may not be VHDL. I think I don't know. Because I don't think Yosis, which is the synthesis tool, has really good VHDL support. It's like a front end to it that gets some development, but it's not always up to date. So I think that's the state of it, but I'm not 100% sure.
We had a comment on that where someone said you can use GHDL plugin to convert VHDL into Verilog if you want.
Okay, yeah. So yeah, it's a front end. Okay.
And there's one other quick question. I understand that working locally should be easier if you are on Linux. Is this the case?
Yes. Yes, it is 100% the case because that's what I use at home, and it was way easier.
All right. Is there anything like a VM image with everything set up, or a container that could be used to test all the steps locally?
So this is how it works in the back end. So if you wanted to run literally everything yourself, it's a set of it's like the whole open lane flow is a set of Docker containers that you can run. You can run this on Windows, but you have to have WSL2 installed and some sort of like containerization system. So yes, you can. The problem with trying to make a container with everything in it is then you have the subcontainers, and that's like with Docker is, from what I understand, a little bit tricky. So I was trying to set that up on my Linux machine before and have that ready for everybody for this, but I was running into issues even trying to get that to work on Linux with getting like all the pass-throughs and stuff working for the containerization. So yes, you can, but that's why I said it was kind of a pain. It's available. You can actually, so if you're motivated enough, you can sort of figure out what Tiny Tapeout's doing by looking at the GitHub action scripts and seeing how that all, like what it's doing in the background to run Tiny Tapeout. You can do all of that locally on your machine. It's not too bad on Linux. It takes like a day to get set up on Linux, from my experience at least.
So you're saying if someone figures out how to do it on Windows, that would be great.
Yes, yeah. Yeah, you can do it. It's possible. And if somebody does it, please document it and send me an email because I would love to know. But yeah, it's a little harder. Okay, so iVerilog, we're going to run the simulator. So we're going to run test and oops, you'll see. Sorry, too early. Test and then tb.v. Yeah, it's okay. It's okay, Chris. I'm not done yet. Okay. Sorry. Test tb.v. We're going to include all our source files. So we're going to go to source, and we're going to do and then source fib.v. Okay, there we go. We're going to run that. And this is going to run, and it's going to generate us a output. And then what we can do is we can run the simulator. So VVP, and it's going to be tb.vvp. So that's going to run. Oh, okay. And then we should be able to look at GTK wave. And then it'll be tb.vcd. And then test tb.gtk. TKW. And that should pull up, yeah, GTK wave. Okay, it looks like that didn't quite simulate correctly, but I do have an extra dump window.
And real quick, Sam, you have all this documented in the slides as well.
Yes, this is all in the slides. So that was like the slides that we just went through. And this is just me trying to make sure that try and show that it's working live. So we can go here, can open that up. And this is a dump file for that. And we can go through and we can look at all our signals. Shift, yeah, there we go. Control, it's gonna, yeah, there we go. There's our signal, UI in, and we can, basically you can just use this and you can look at all your signals. So that's basically how you run the simulations locally. So you basically have you can even run it, like I'm running this directly off of a flash drive. So what we can do is, even on our website, I have links to all of where all this stuff is. You basically download a zip file, you extract the zip file, and then you have this folder, and then you can start that, and then all these tools are there. That makes sense? It's not too bad to get started in, as long as you're not live. Okay. So with that, we will get back to the presentation. I'll run through the rest of this really fast because I know we're low on time. So yeah, next steps. So want to install just the simulation tools locally, follow some digital design guides. Verilog tutorials are available that you can use to get started learning the Verilog syntax, etc. And then you can test all your own designs. So this is a bit more of step-by-step instructions that has links to everything for you. And I'd recommend that you try and recreate that Fibonacci sequence generator that this example project. You have my example code that you can look at as well, but it's really beneficial to like go through and do it yourself. So this is what I recommend for doing your code. So you just install stuff. You set up a Tiny Tapeout project with GitHub. You write your Verilog code. You simulate. And then you can push the design to GitHub, and that'll spit you out a GDS file that you can look at the cool 3D render to. So where to get help? So probably the main place I recommend getting help from is the Tiny Tapeout Discord. It's filled with lots of people with deeper knowledge than me about digital design, and I'm there too if you want to ping me for some reason. But yeah, QR code right here. If you there's some good learning resources. Tiny Tapeout has links to some. We have resources available. I haven't put all of them up on the website yet because I was busy making slides. But resources are available. Good resources are available to learn Verilog and things about the digital design flow. And if you have other questions as well, you can feel free to email the chapter, which I get that email, and I think everybody here gets that email. So yeah, Tiny Tapeout, Discord, really good resource. Acknowledgements, Matt Venn for the original workshop slides that these are based off of, and advice on running a workshop, CAS, Sensix, and everybody who worked on Tiny Tapeout. So yeah, with that, yeah, and this is just QR code links to the sponsorships and yeah, event feedback. Really like event feedback. Want to learn, figure out what we can do better for running these workshops in the future. This is my first time running a workshop, so yeah. So that in mind, yeah. Questions?
Just to get an idea of like what's capable with Tiny Tapeout, do you have any examples of like really cool projects people have done?
Oh yeah, I probably should have included that in the slides. There's some people who's done fun things. So this did not fit into a single tile. Somebody ate up a whole row on Tiny Tapeout and made a Linux-capable RISC-V processor. So like that didn't fit in like a single tile area, but like with that's 16 tiles. You can RISC-V capable Linux, or Linux capable RISC-V, the way they say that. People have made like in a single tile. I think Matt Venn has an FPG, or not an FPGA, a VGA clock. So like he made a little clock and that outputs to a VGA display. the example project I want to run through for the rest of this workshop is just a little digital desk clock with using like LED segment displays. So like being able to fit on there, like you can set the time, it'll display the time nicely on a set of LED displays. And I think there should be enough room to put in like an alarm clock feature into there too. But I didn't want to, like, making the workshop, I don't want to have too much, try and pack too much into it too short of a time. So yeah, so that's an idea. There's been other neat projects, and they just, in this last Tiny Tapeout, they've just enabled analog and mixed signal designs. So if you want to be really adventurous, there's that. So that's basically, you just provide Tiny Tapeout a GDS file, and they'll hook it in. So you can do the design with that in any way you want. So this is using the digital flow. Okay, yeah, there's another question before I just continue rambling on. But yeah, so that's sort of, you can do a lot of cool stuff. And if you go to the Tiny Tapeout website, they have a list of all the past projects that you can look at.
So this is a quick question related to the PICO Chipathon. Do I need to know analog IC design to participate? I am a sophomore and I have had only a basic analog electronics and basic digital VLSI design course, but no experience with analog layout.
Yeah, can you take that, Gus?
So the answer is no. You just need to write a proposal, and it's very hands-on, actually, with Dr. Merman and the rest of the experts there. So they meet with you weekly, and they accept proposals from all skill levels, even high school students with no prior knowledge. So yeah, the answer is no. You can start from any level.
All right, another quick question. What other common utilities does the taped out chip feature? Currently, you have mentioned the muxing that selects your design to interact with.
So I think it pretty much just wires the inputs from the digital inputs from the outside world into your chip through that mux. There are in the test board, if I can go, oh, you know what, I can do this. Oh, I can't see anything.
Sorry, my laptop's slow.
I can go up here. It's around in here. Yeah, it's around here, something like this. Okay. Yeah, okay. So if we go up to here, there's in the test PCB, you get a Raspberry Pi 2040 that's basically controlling your Tiny Tapeout chip. So it is going to control your clock signal. So it'll push in your 50 megahertz clock into your chip, and it'll control all your input output pins if you so desire. You can also kind of just wrap them out to the outside world. I don't think the Tiny Tapeout chip itself, like the actual hardware here itself, actually provides you a lot of functionality. I know there was talk about adding in a memory cell, but I don't think that's going to be available in the designs that we're looking at.
All right, that answered the next question, which was whether or not there was some on-chip memory for buffering.
Yeah,
data.
I don't think there is. There is, I think, internal buffering so that you can make it through the mux in like a reasonable time frame, because the design goal is that you should be able to hit 50 megahertz through Tiny Tapeout. So your I/O should be 50 megahertz capable. But I think that's pretty much the only guarantee. I don't think there's any like pipelining that goes on inside of Tiny Tapeout or anything like that.
Another quick question. You mentioned the fact that Tiny Tapeout process is suitable for analog. Is there any tool and provision to actually do mixed mode? Will there be any workshop specifics about this?
I'm not going to cover it. We'll put it that way. There are tools.
Hello, Sam from the future here. Just an update on installing the analog tools. There is in fact a VirtualBox VM for installing them. It's a 20 gigabyte install. Links will be in the description of the video.
Again, Tiny Tapeout Discord is a good place for this. Because the analog tools are there. So in terms of doing analog design, there's Xscheme for doing the analog schematic capture. And then there's ngSpice for doing analog simulation. And then you can run through either KLayout or Magic for doing your layout and things of that nature. So you can get all those tools installed, but they're not nearly as nicely packaged as the digital tools. So like for the digital tools, if we want to run simulation, we just install the like open source CAD suite, and then we just have them. You basically have to do all the work for like install the whole flow for doing the digital flow in order to do anything in terms of doing the analog flow. So you have to have basically everything in terms of doing the analog flow. So you're committing to doing the 10 gigabyte install and all of that. There is like a Docker image for this. I think it's who maintains that. I cannot remember off the top of my head, but that is available. And since Tiny Tapeout's starting to incorporate the analog mixed signal design into it, they're adding more documentation onto the website. This last Tiny Tapeout run was the first official run with analog mixed signal support. So they've added a bunch of documentation to their website, and they've been supporting it in the Discord server as well. So hopefully that answers that question. Maybe in the future, maybe next year, I'll understand the analog flow well enough we can cover it, but not right now.
And along that lines, for analog circuit layout, is layout tweaking possible?
In terms of doing it in the digital flow, or in terms of doing it in the analog flow?
I would assume the analog flow. So I would assume at that point.
Yeah, you're doing the layout with like say Magic or KLayout. So yeah, you can control the layout. Okay. Other questions? So yeah, I'm going to go back to the end here, and we can show the QR codes again. But
while he's pulling that up, for everyone that's local, if you can please fill out the QR codes, and everyone online. And for the local people, we'd love to take a group photo to show that people came in person. And online people, if you want to take a selfie and email us, we'll stitch it in. I won't do it. I'll have someone else do it.
Yeah, it would be me putting it on the website. But yeah. Okay. Thanks, everybody. Fun.